Firstly, we'll need to open Comsol Multiphysics. Note that while there are several versions of Comsol installed on the Mind's computers, and a number of those also contain multiphysics, it's easiest if you select the Class Kit license version. This may take a while to load, but once it's done, you can use the model wizard to generally define the simulation you'd like to create. We're modeling the Krogh blood diffusion problem, so if you haven't already viewed the related PowerPoint file, please stop this video now and go do so. We'll start by selecting a 1D axisymmetric geometry. This aspect, axisymmetric, is crucial to the accuracy of your model as it recognizes that r equals 0 is the center line of a cylindrical system and not simply the origin in a Cartesian system, which as we know affects our differential equation and integrals among other things. Next, we'll choose the transport equations we'd like to model. Choose the only mass transport option, but note that in other versions of Comsol you would have a number of other options under this heading, including transport of concentrated species, Nernst-Planck equations, porous media transport, etc. You can either double-click this option or select it with a single click and choose Add. Note, we could add another species balance here, which by default would have a concentration given by C2, but in this case we're only concerned with one species. After clicking Next, we come to the final option of the simulation settings, time dependence. As is tradition, we'll go for the steady state solution of this system. So go ahead and click steady state and then click Finish to create the simulation file. Now that we've got a simulation, we need to define the geometry of our model. Click on the Geometry tab in the toolbar at the top and select the interval icon from the Draw section in the toolbar. Because the simulation is restricted to one dimension, it doesn't matter where you align the mouse on the y-axis, only the x-axis location matters. Click once for the left boundary at approximately 0.05 meters, and then again for the right boundary at about 1 meter. If you do this in the reverse order, that is right to left, then your boundary ID numbers will be the opposite of mine. That is, number 2 will be number 1 and vice versa. After completing the segment, a dialog box will pop up on the left side which allows you to refine the geometry you've drawn. As you can see, I drew the segment from the origin at r equals 0 meters instead of 0.05, so I can manually update that value here in the starting position to 0.05. But note that the geometry will not be automatically updated until I click on Build All Objects. Don't forget to do this after making any and all changes to the geometry. Once rebuilt, you can click on the Zoom Extents button in the graphics window to focus the window on our line segment. Now that our geometry is defined, let's define our global parameter, the reaction rate, by right-clicking on Global Definitions and selecting Parameters. Note that you can use the Global Definitions sections to define many things, including constants, parameters, functions, and other useful stuff. Once the parameter dialog has popped up, we can define our reaction rate parameter by giving it a variable name, I, and a value, 0.02. This parameter is dimensionless, but we'll see that it will gain units where we apply it to the model. You may choose to define this parameter in the description section, but this is not really necessary for simulations with only one parameter. Now we can move on to the boundary conditions of our model. Under the heading Transport of Diluted Species, we can see that the default BC for both boundaries is the no flux condition. Go ahead and click on No Flux 1 to verify this, and you will see that both number 1 and number 2 are selected. When we define a new boundary condition, below this one, it will override this default, but you can check this later yourself. If you right-click on the heading Transport of Diluted Species and click on Concentration, we can define a boundary condition of constant concentration. And now, if you click on the left point, the inside radial boundary, it will automatically be added to the list. When you click on the boundary number in the list, the point will turn green in the graphics window. If you select the checkbox by concentration, you can then fill in the concentration value of 1. As you can see, the units for this quantity are already specified as moles per cubic meter. If you want to enter alternative units, you could do so by adding them in brackets after the value of 1, but we'll see this in a second with the diffusion coefficient. Now that we've defined our two boundary conditions, we need to define our domain settings, that is, the material properties which govern transport between the two boundaries. Select the section Transport Properties under the same heading, and we'll see the options we have for this section. Verify that the velocity field in the r hat direction is exactly equal to 0. Our model assumes zero convection, but for another model you could either define the velocity function yourself or use a momentum transport simulation solved simultaneously to provide this velocity field. Finally, we're going to modify the diffusion coefficient from 1 times 10 to the negative 9th meters squared per second to 1 meter squared per second. Here you can see how to provide units between square brackets in your expression, although in this case the specified and the required units happen to be identical. Note that you must write m caret 2 and not m2 for meter squared, and that exponential notation is just as in Excel. You should also know that Comsol doesn't recognize any and all units, for example nanometers, and you should verify that the units you want to use are recognized and computed correctly. Finally, we need to add our reaction rate to this domain. Do this by again right-clicking on the heading Transport of Diluted Species, and this time selecting Reactions. Once you select the line segment, or modify manual to all domains, the domain number 1 will be activated for this reaction. If you expand the equations section, you can see where the reaction term shows up in the differential equations Comsol will be modeling. Note that you can do this in the transport properties and for each of the boundary conditions as well. Enter negative 4 times I for the reaction rate. Note that 4i will yield an error, while 4 star I, again in Excel notation, is the proper expression. We include the negative sign to indicate that this is an OT consumption rate and not a production rate. At this point, the model is complete and you could generate a solution for I equals 0.02. However, we'd like to explore the effect of the reaction rate on the model results, so we're going to specify a range of I values to evaluate. So go ahead and right-click on Study 1 and select the Parametric Sweep option. After the dialog pops up, click on the plus icon and the only specified parameter in the Global Definition section will appear in the Parameter Names column. In the parameter value list, you can enter either a list of values, for example 0.05, 0.1, 0.15, and 0.2, or a range expression which will test values at regular increments. In the range dialog, the arguments are initial, step value, and final. You can leave the units blank again because we are using I as a dimensionless parameter. Next, we need to build/initialize the mesh. Herein lies the magic of the Comsol software, finite element modeling. The domain, our line segment, is broken up into mesh points in which process values, for example concentrations, fluxes, etc., are averaged. The finer the mesh, the more precise the model, but also the longer the calculation time will be. For our first try, we'll go ahead and use the normal element size. So right-click on the Mesh 1 heading and click Build All to build the mesh of 15 discrete elements. At this point, we can modify the element size to be finer, either in the dialog or via the toolbar up top. But remember to click on Build All again to rebuild the new mesh before continuing on. Now that we're ready to run the simulation, we'll right-click on Study 1 and click Compute. After a short time, depending on how fine you've made your mesh, you'll get the results in the form of a color-coded graph of concentration distributions for the various I values along the length of our line segment. There are several things to note in this section, the first of which is the Legend option in the Settings dialog box. If you click the checkbox, you can add a prefix to the legend, which otherwise just lists the parameter values, such as this one, I space equals space. You can also remove or add the legend using the icon in the graphics window. The second item which you should note is that the x-axis measures the distance from the leftmost boundary of our line segment and is not the R position. To change this, select the x-axis under Grid and modify arc length to expression in the pull-down menu, and then enter R for the expression. You may use other expressions or formulas here, but right now we want the distribution on the R-axis. If we click on Plot again, the graph will be replotted with the new proper x-axis values ranging from 0.05 to 1, instead of 0 to 0.95. Note that you may select from a list of predefined units for this axis. When you're done editing the graph, you can click on the camera icon to create an image snapshot, which you can then paste into another application. Note that there are a number of options you can select to modify the image output, including saving to a file, for example a GIF or a PNG file, instead of just copying to the clipboard. In order to export this data to Excel, however, you must first port the data from the graph to a table. Do this by right-clicking on Line Graph 1 under the heading Concentration TDS on the left-hand side panel, and then clicking on Add Plot Data to Export. After this, a new section called Plot 1 should have appeared under the Export heading on the left-hand panel. The dialog box for Plot 1 should have the correct defaults selected, concentration for the plot group and line graph for the plot to be exported. You need to select a file for the data by clicking on Browse, choosing a directory, and typing in a file name. Note that you can choose among a few options for file extensions, including .csv and .txt, either of which should work for importing into Excel. Next, we need to import the data into Excel. We'll do this using delimited format, including spaces as the delimiting character. Even though we've chosen a parametric study, the export tool from Comsol is not so elegant that it will sort our data for us. Instead, it will come out in one long list of X and Y values. You will need to manually sort them into separate columns to graph them in Excel, i.e. with cut and paste. Just scroll down to where the X coordinates restart, that is at r is equal to 0.05, after the last measurement of r is equal to 1.0. Select the remaining data to the end and paste into the neighboring columns, and then repeat to generate the full table. As you'll soon see, the data was imported in the order of the parametric study. Thus, you can safely delete all but the very first column of R values and plot the various concentrations against this single column of R values. Once this is done, you can now generate analytical data from the theoretical solution in the neighboring columns, against which you can compare the numerical results produced by Comsol quantitatively and also graphically if you so choose. Finally, let's turn back to the Comsol interface for one more type of analysis of our results, that is, calculating average values. Recall that evaluating average values requires integrating that value over a given volume and dividing by the integrated volume, and also that this turns out to be very different for curvilinear axes than for Cartesian. This is because the determinant of the Jacobian for spherical coordinates includes r squared, and that for cylindrical includes r. Or, in other words, the concentrations near the outer radius of this blood vessel occupy a larger portion of the volume than the concentrations near the inner radius, and thus are more heavily weighted when calculating the integrated average. To calculate an average concentration, right-click the heading Derived Values, select Integration, and then click on Line Average. Select the domain, that is our line segment, in which you'd like to calculate the average value, or simply choose all domains from the Selection pull-down menu. Verify that the concentration expression C is selected and the desired units are depicted. Next, expand the Integration Settings section and check the Compute Surface Integral box. Note, if you do not check this box, it will integrate the concentration over dr and divide by the length of the segment. When you do check this box, it will integrate the concentration over 2 pi r dr and divide by the total area, pi r outer squared minus pi r inner squared, where r outer and r inner are 1 and 0.05 meters in our model, respectively. To complete this step, click on the Evaluate button to produce a table of average concentrations for each of the parameter values I. Note, if you try this again without the box checked, you can see the effect of this curvilinear integration on the average values in the table.